I'm going to just summarize a few things about logarithms. So logarithms are really just asking how many magnitudes or multiplications of the base, usually we use base 10, so how many magnitudes or multiplication of 10 fit into that number, or how many multiplications or magnitudes of it's not base 10, whatever that base is, how much that fits into the number. So for example, if we have log of, again, we have log of 1000, we're asking how many magnitudes of 10, when the 10 isn't written, we just assume log base 10. So how many magnitudes of 10 go into 1000? Let's say this is log base 2, then we're asking how many magnitudes of 2 go into 1000. But anyway, when it's log base 10, we know that 10 times 10 times 10 is 1000, 10 to the third is 1000. So it's basically asking how many magnitudes of 10 fit in this, how many multiplications of base fit in that number. And this is really useful because we're able to express things as a magnitude. And the logarithms, we use this in many different situations. We might ask, well, if this is the inverse of exponents, why don't we just use exponential functions? But the reason we use logarithms is because sometimes things might have a logarithmic relationship, which is the opposite of an exponential relationship, which I'll show in the graph. But we want to be able to represent some things and see it from the perspective of magnitudes. So, for example, pH, we might want to see pH from the perspective of magnitudes of 10. We might not want to see pH. pH scales range from 10 to the negative 14 to 10 to the 0. And 10 to the negative 14 is a really different number than 10 to the 0. They're really small numbers. And to be able to visualize that difference, we want to visualize it as magnitudes of 10. So that's why we take the log base of the negative log base of it and obtain a normal positive pH scale of 0 to 14. So similarly, we might want to not just visualize numbers as they are, but rather visualize magnitudes. So we might do that in many different examples and situations. For data, we might want to take the log scale of a plot and want to visualize it that way to be able to visualize magnitudes of certain base. So we can have different bases, but we use base 10 a lot in many different situations, such as example, the pH scale. And so with logs, when we're calculating logs, yes, we're looking at how many magnitudes and multiplication of base fit in that number. And when we're in log base 10 at least, that's basically the same thing as saying how many places do we move to the right or left of 1. So for example, if we have log of 0.0001, well, we're moving 1, 2, 3 places to the left. So if we make the left, it's a negative number, so it's negative 3. If we're using 1000, we're moving 1, 2, 3 places to the right, that's 3. But again, that's in log base 10, that's a trick to be able to use. But know that this is just the same thing in asking how many magnitudes of 10 go into 1000, how many magnitudes of 10 go into 0.001. So you can really just think of this as 10 to the 3, because that's the same thing as 1000, and this is really the same thing, 0.001 as 10 to the negative 3, or 1 times 10 to the negative 3. And so we're asking what power do I have to raise this base to be able to get this? And so if this is base 10, obviously to raise 10 to the negative third power to be able to get this value, and same thing here. And so that's basically how you can think about logarithms. You can think of it as magnitudes, a number of zeros that you're trying to move in a log base 10 system. But really, if you just think about it as magnitudes and how much the extent of base that I want in that, that's really going to come in handy. And so 3 things I'm going to go over just to understand about logarithms. So in a previous video, I summarized about log tables, and I showed in the olden days they used to be able to use this multiplication problem. If there's this we can do by writing it out, but even if you had an even longer multiplication problem that might be more tedious, you might want to use log tables to be able to express this as a power of 10 in base 10. So again, it's like a magnitude. So what power do I have to raise base 10 to be able to get 37? And we would look at it in the log table, and there are techniques that people use to be able to calculate these exponents. And so you would just search up in the log table, and you would get that 10 to the 1.5682 is equal to 37, or actually it's 10 to the 0.5682 is equal to 3.7, and you know that you add one more magnitude 10, so 10 to the 1.5682 is equal to 37. And you would do the same thing with 58, and then you would write that out, and then you could be able to add these exponents because they're both in the same base via exponent rules. So in this way, this is really in log tables, by using logarithms, we're able to turn multiplication into addition, we're able to turn division into subtraction. And you can see how logarithms are useful because we're able to shift operations. We're directly able to shift this multiplication problem into an addition problem. What calculation are we doing in here? I mean, these are things we would search up on the log table, right? Or we could just understand based on intuitively knowing that 10 to 0 is 1, 10 to the 1 is equal to 10, and knowing where this stands and how do you get 10 to the 0.562, that will get in the middle, so around 3.7. So we could do that, and we can look at the log tables and understand these and get these exponents and be able to turn this multiplication problem into addition. We also turn division into subtraction. So this is a really key concept. And also know your log rule. So log of a divided by b is equal to log a minus log of b, log of a minus log of b. So in that way we're turning division into subtraction. Log a times b is equal to log a plus log of b. So know those rules, and the other rules you can really tell by the exponents, and if you're understanding how logarithms are basically asking how many magnitudes of multiplication of this base fit in the number. So again, that's the first part that we want to understand. The next part is really looking at the graphs really help. So first, what function is y equals log of x? So really, y equals 10 of x is the exponential function that we see when we're graphing something like this. So you can see here, this is y equals 10 to the x graph, and this is an exponential function. And I showed in a previous video that is you increase the amount of the exponential growth. If you go from y equals 2 to the x, y equals 10 to the x, and you just keep on going y equals 100 to the x, and you keep on increasing these by magnitudes of 10, you just keep on increasing. This never really approaches the origin because 0, 1 is always at a point on there. It's always come here, and it's going to go up like this. So it's an exponential growth curve, and so that's how we see this exponential graph y equals 10 to the x. And so what this is doing is when we go into the log system, we're just putting it in a different form. So we're just taking this, we're doing x is equal to log y. So we're reversing this and then saying x is equal to log y. So this is the system that we get to be able to convert from the exponential function to the log function. And you can really see that, let's say for example, if you do, again, let's do our same example. If you do y equals 10 to the third is equal to 1000, what you would do is to be able to shift this to a log form, you would just do log 1000 is equal to 3. See, and this is base 10. So you can see this is our base, and then this is the power that we're raising it to, and this is our result, the argument. And so what power do you have to raise this base of 10 to be able to get 1000? Or aka, how many zeros to the right of 1? That's 3. And so just understanding that, you can be able to convert these exponential ones into the log format. And so that's what we're doing here. Y equals 10 to the x. We convert that. Just imagine this is 10 to the third equals 1000. What would you would do log of y, log of 1000 is equal to 3, right? So that's the same thing here. Log of y is equal to x. And so that's what you get this graph. And so these two graphs are the same. Y equals 10 to the x equals log of y. That's what this graph is, right? That's exactly what this is, right? Exponential increase. And similarly, when we have 10 to the y equals x, if we reverse that, we just do that and we get y equals log of x. And so that's this graph. And that's this one, right? And you can see how they're inverses of each other. Because really y equals 10 to the x and 10 to the y equals x, all you're doing is really shifting x and y. Same thing, x equals like a y equals log x, what are you doing? Shifting x and y. So what you really should remember is this, that the exponential graph looks like this, exponential increase, y equals 10 to the x, and then the inverse of that is y equals log of x, and that's this. And that's the same thing as 10 to the y equals x, so that's y equals log of x is really the inverse of that. And you can flip it, so you can see that even the points, so you can see that on the y equals 10 to the x graph, the exponential graph, there's a y-intercept 0, 1, that's always a fixed point on any exponential graph. The inverse of that is 1, 0, indeed on the inverse graph you have 1, 0, log of 1 is 0, and that's a fixed point. Also know that log of 10 is 1, because 10 to the 0 is equal to 1, 10 to the 1 is equal to 10, right? And so those are 2 points on the log base 10 graph, log of 1 is always equal to 0. And so we have this, so we can see how these are their inverses of each other. So being able to visualize the graphs is really important, and that's why I wanted to show here that, again, y equals 10 to the x, that's our exponential function. If we take the inverse of that, we get x equals 10 to the y, and whenever we're taking an inverse, we're going into we're really just shifting x and y, and so that's what this is. But y equals 10 to the x, if we go into the log format, when we're going down here, I'm just literally doing the same thing as I did. 10 to the third is 1000, log of 1000 is equal to 3. That's really the same thing, 10 to the 3 is 1000, then you do log of 1000 is 3. That's in the variable format, that's what I'm doing here, so 10 to the x is equal to y, log of this result is equal to the power, that's what this is, x is equal to log of y. Similarly here, x equals 10 to the y, and then I do the same thing, so log of x is equal to the power y, and so I get this, and you can see how these are inverses of each other just by the exponential graph is an inverse of the log of x graph, and so these two are the same, x equals 10 to the y, y equals log of x, y equals 10 to the x, and x equals log of y are the same, but we're taking the inverse of it. So really, again, just remember these two, that y equals 10 to the x, how it looks, the exponential graph, and remember how y equals log of x looks, and that's really helpful because you can, visualizing the graph, you can tell a lot of things. For example, even like in the y equals log of x graph, you can tell that anything below, any x value below 1, your y value will be negative. And so that's, if you have, for example, if you have a log of a fraction, log of 1/2, that'll be below, it'll be below, log of 1 is 0, so it'll be below 0, right? Because you know that the y value here is 0, so you know that any fraction below 1, if the x value, remember this log of x is equal to y, so if this x value is less than 1, you know that the y value is negative. And so that's really helpful to know. You can be able to calculate any log functions. You also know, if you know your log rules, you can just flip log 1 and 2. Instead of log of 1 divided by 2 is equal to log of 1 minus log of 2, you can also put the negative sign and then flip them and do negative log of 2 over 1, and so negative log of 2, and you can be able to get that. So based on this, understanding these graphs can really come in handy. And so even that, again, what I'm showing here again, if you're flipping these 10 to the third is equal to 1000, you literally flip it, log of 1000 is equal to a power. Again, this is asking what extent of the space fits into this result. And so you can see how it's literally the reverse of the exponents. And you can also see, indeed, at points, like I said, 0.01 on the 10 to the x graph, on the exponential graph, that's intercepting the y-axis. On the other graph, on the y equals log x graph, that point is inverse, so your x is equal to y. It flips over the line. This graphs actually flip over the line, y equals x. So if you have a line like, if I draw it right here, this is actually flipped over. It's a straight line, right? And this is y equals x, right? And so that's this graph, this y equals x exponential graph is flipped over this line y equals x to get the y equals log of x. And so you're literally just switching x and y, so you need to switch x and y. And so on this graph, again, it's a y-intercept. On this graph, it's actually an x-intercept. So log of 1 is always equal to 0, and then 10 to any power to the 0 power equals 1. So 10 to the 0 is equal to 1. And so understanding the graphs, you can tell a lot of things. Again, so y equals 10 to the x and y equals log of x are inverses of each other. The exponential graph is an inverse of this y equals log x graph, and that's basically saying the same thing. They're mirror images of each other on the graph, and they flip x and y. And again, so if in looking at these logarithm functions, so you know that 10 to 0 is equal to 1, 10 to the 1 is equal to 10. So looking at our points, you should know that if you do the reverse, you know the log of 1 is equal to 0. That's a point, and log of 10 is equal to 1. And that's a fixed point. And so if you write that out, 1, 0, and 10, 1, so you can basically get a lot of log values just knowing between 1 and 10, because anything you make multiples of 10 and flip it and really be able to estimate different log values as I showed. So I know that anything below log of 1, so between 0 and 1, log of 0 is actually undefined because you can't take anything to the power and get a 0. You can't take anything no matter what basis is. You can't get a 0 result if it's an exponential graph because 0, 0 isn't a graph on the exponential graph. So log of 0 is undefined, but anything between 0 and 1, if you have a fraction. So eventually, if you see the Henderson-Hasselbalch equation, that's pH, I won't go too in depth, but pH equals pK plus log of A minus over HA, right, of your conjugate base over your acid. Right, if you have this as a fraction, you know that whenever it's a fraction, it's actually negative. So whenever you have a fraction of a log, if it's between 0 and 1, it's going to be a negative value. And indeed, yes, you see that on the graph, again, when it's right here, if you have a negative value between, when it's a negative value, whenever it's less than 1. And it never touches 0, so log of 0 is undefined. There is no y-intercept on the y equals log of x graph. There's an x-intercept, there's no y-intercept. And same thing here on the exponential graph, indeed, you can see there's a y-intercept, it's an inverse, but there's no x-intercept. And so anyway, y equals log of x, yeah, indeed, between 0 and 1, you have negative values. Anything above a 1, you have positive values. And so that's what you have here. Log of 1 is 0, log of 10 is 1. So if you know this, you can guess anything between 1 and 10, and then everything else you can basically estimate. You can just, if you are trying to estimate, for example, log of 200, you can just think of that as the same thing as log of 2 times 10 to the 2. And log of 10 to the 2 is just 2, and so you just use your log rules and just do 2 log plus 2. And if you know everything between log of 1 and 10, log of 2 is 0.3, that's about 2.3. So you can basically estimate any values by splitting it up, just by knowing between log of 1 and 10. And even if you don't know it, again, you can estimate it. So if you know log of 10 is 1, and log of, you just take the next magnitude of 10, so you just know log of 100 is equal to 2. So you know any value between 10 and 100, it will be between 1 and 2, and know that it's that logarithmic function. It's really rapid increase in the beginning, and then after 1, the increase is still rapid in a little bit in the beginning, but then it starts to slow on the graph. So here it's really here it's really rapid increase, and here it starts to slow. And that's the opposite of exponential function. It's rapid increase in the beginning and starts to slow later on. And so that's the difference between exponential and logarithmic functions. Just know just know this: log of 1 is equal to 0, 10 is equal to 1. If you're able to memorize the values that I provided in the previous video, log of 2 to 9, that would be good too. And log of 3 is equal to 0.5 is in the middle of that, 2, 0, 1. And then anything below between log of 0 is equal to undefined, and between log of 0 and 1, any fractions, you're going to have negative numbers. And you can also think of this as log of 1 over half again. You can flip these. So if you write it out, log of 1 half again is log of 1 minus log of 2 is equal to, this log of 1 is 0 and negative log of 2, so 0 minus 0.3 is negative 0.3. Or again, you can flip this and then add the negative sign out here. So you can do log of 2, you can then put the 1 in the denominator, and when you flip them, you add a negative sign. So I'll just to write that out, log of 1 half is equal to negative log of 2 over 1. So when you flip the numerator and denominator, you just add the negative sign out there. And so you can really estimate anything like that using this values, and you have a better sense of what logarithmic functions do. And so again, just keep in mind that right till now I've been mainly talking about base 10, but you can have other bases. When you have ln of x, that's really base e. So natural log of x, you might see that commonly. So ln of x, that's really the log base e. And people also use base 2, and so these values might be different for those different base systems. But just understand that log is like taking the magnitude. So what amount, it's normalizing it to that base. So what amount does that base, what extent, how many powers of that base will fit in that result, or whatever I'm looking at, whatever number I'm looking at. So what magnitude or extent of base it is in that result, what power do I raise that base to get that result? That's what logs are. And you can see how this is the reverse of exponents. And so people often ask, like, yeah, why the log function is useful? Why can't we just use exponential function? And so we can take the log scale of points of data per graph to be able to better understand the relationship between the magnitudes of what we're studying. So for example, if we're studying something that has very, like the pH scale, for example, it's very, very different numbers, 10 to the negative 14, 10 to the negative 12. If we want to understand the difference and normalize it to base 10, we can normalize it to base 10 and be able to see the differences and understand the magnitudes between what we're studying. So we want to be able to understand it after normalizing it to based on a certain magnitude. So in the pH scale, for example, we're normalizing to base 10, and we're kind of 10 to the negative 14, we're just looking at the exponent of 14, we're normalizing the base and really looking at the magnitudes of hydronium ion concentration. Because 10 to the negative 14, 10 to the negative 13, well, when you go from 10 to the negative 14 to 10 to the negative 13, you're increasing by a magnitude of 10 by 10x hydronium ion concentration. And that might be really hard to see on the pH scale, but if you don't use the pH scale, you can just see like on 10 to the negative 14 to the left of 1 to less than 1, so that means you would have 13 zeros, or 14 places to the left of 1, and 13 you would have 13 zeros, and you have 12 zeros, sorry, at 10 to the negative 13 and 13 places to the left of 1. And to be able to see the difference between the number of zeros on that might be hard to visualize. And even 10 to the negative 14, 10 to the negative 13 is kind of going to write, but if you take the negative log of that, you can just write pH 13 and pH 14. So between pH 13 and pH 14, you have a 10x difference, but you're able to normalize it to the magnitude of base 10 and visualize the differences. So that's why logarithms are helpful, to be able to visualize magnitude. So whether it's writing stars, whether we're looking at sound and the decibel scale, when we look at the magnitudes of sound, and we normalize it to a base, and we're able to study that graph from that. And also another reason is the logarithmic relationship is different from an exponential relationship. So you can see an exponential relationship is here. It starts off the increase. If you take the derivative slope of the tangent line, you can see in the beginning the increase is sort of slow, right? If you take the tangent line right here, it's not that steep, but eventually, especially after 1, 0, things exponentially increase. The slope gets higher and higher and steeper and steeper. And so the increase starts off slow, and then it gets rapid increase later. Logarithmic function is opposite. So an exponential function, we start off slow, we end fast, and the logarithmic function, we start off fast, and we end slow. So here you can see the rate is just the line, the derivative slope of the tangent line is really steep, and eventually, especially after 1, 0, slope really starts to decrease, and so you're getting slower and slower, and so the rate at which we're increasing is decreasing in the log function. And so that's what the difference is. They're literally inverse of each other. Logarithms, they basically undo exponential function, they're the opposite. So just like subtraction is opposite of addition, and division is opposite of multiplication, log of x graph, the y equals log of x graph, is basically the opposite of exponents. And so we can see again the difference in relationship. You might have something that falls a logarithmic relationship and not exponential relationship. Really quickly, we can be able to visualize that and understand it. So that's the difference between these two. So again, I just wanted to really convey the graphs and the meaning of those because it's really helpful to understand. And so lastly, again, I already went over this, but all log is asking how many magnitudes of this base fits into this. And if it's a number greater than 1, the number of zeros will be equal to the number of places, or the magnitude. If it's a number that's less than 1, the number of zeros will be 1 less than the exponent. So for example, here, usually in scientific notation, we write 100. We write 100 as we write it as exponent and between a number of 1 and 10. So we write it as we write 100 as 1 times 10 to the 2, right? This number should be between 1 and 10 for scientific notation. So this is basically saying that we're going 2 places to the right of 1 to be able to get 100, right? 1, 2. That's what this 2 is saying. To be able to, that's what scientific notation is. So again, this number is indicating the number of zeros if it's a number greater than 1. If it's a number less than 1, then the number of zeros is 1 less than. But in this situation where the number is greater than 1, it's the same number of zeros as the exponent. And again, how many magnitudes of 10 fit into this? That's 10 times 10 is 100, so it's 2 magnitudes of 10. And so you can think about it as magnitudes or 0. As long as you think of it that way, you can really understand logs what they are as when you think of them as ratios and magnitudes. So if you have, for example, again, if you have log of 10 to 100,000, that's how many magnitudes of 10 fit into 100,000. Just looking at the number of zeros, it's 1, 2, 3, 4, 5. How many places do I move to the right of 1? 1, 2, 3, 4, 5. That's the same thing as number 0 is 5. So your answer here is 5, right? Here the answer is 2. Here the answer is 5. And so, again, number 0 is to the right of 1. That's what this is. And so when you have a number that's less than 1, however, if you have something like this, the number of zeros is 1 less than. I mean, if you count the zeros, the number of zeros is equal, but anyway, the decimal places to the left of 1, it's 1 less than 0. So in this case, remember, you have to move to the left, so that's 1 place that's given up there, and then you move 2 more. And so the number of zeros is 1 less than the exponent. So if you have 3, you have 2 zeros here. If you think of the 0, then you have the same number of zeros, but you don't really think of that 0, right? You don't have to write, that's just point, that's decimal. So the number of zeros, whenever it's a number that's less than 1, the number of zeros is 1 less than it. But as long as you just think of this number when you're base 10 system, negative meaning you move to the left, how many places you move to the left, positive meaning how many places you move to the right. That's consistent no matter what. So negative 3, you're moving 1, 2, 3 places to the left, and that's 1 less 0, so 2 zeros. Negative 2, you're moving 2 places to the left, that's 1 less 0, that's 1 0, right? 10 to the negative 1, that's 0, that's no, that's zero, no amount of zeros, but you're making one place is still left, right? And so you can also think of that any of these negative exponents, you can think of them as flipping them to the denominator, right? So if you have 10 to the negative 1, if you send it to the denominator, it becomes positive 1 over 10. That's the same thing as 0.1. So this isn't even logs, this is just exponentials and scientific notation. But when you convert to logs, yes, when you understand this, it makes this much easier, right? Because you're seeing how many magnitudes of 10 you have to raise to get this this value right here. Well, the value's the same, right? Same 3. So you can think of this as in log with these 3 or just think of this, what power do you have to raise this base to be able to get this, and that value's -3. And or you can think if you're visualizing in this situation, you would say, how many places do I move to the left of 1 if I have base 10? So that's 1, 2, 3. Or how many zeros I have plus 1 is the exponent, right? So that's 2 zeros plus 1, 3. But because it's a number less than 1, you're moving to the left, it's a negative number. So how many places do I move to the left of 1? 1, 2, 1, 2, 3. That's -3. Same thing here. That's -2. Same thing here. That's -1. Left is the left. And then again, if you have a positive exponent, you're going to the right same number of zeros. And so that's these right here. And so as long as you think of logs in this way as normalizing to a base and visualizing, be able to visualize different numbers as a magnitude of that base and what extent that base, it makes it really easy to be able to understand. And especially if you think about going from 10 to the 3 to 10 to the 5, you're increasing by a magnitude of 10 to the 2. In the log base scale, if you just took a positive log of 10 to the 3, you get 3, right? So for log, when you're thinking of log scale, you're looking at the difference between 3 and 5. So you're looking at the numbers 3 and 5 when you take the log. But when you're looking at without the log, you're looking at the difference between 1,000 and 100,000. So really, logs really be able to emphasize and magnify what's occurring at a difference, which is why sometimes data you would take log scale. Sometimes even taking the log, some people use it to convert it to a linear function and be able to visualize it as a linear function if that equation works out that way. But that would be dependent on the equation that you're manipulating it to be into a linear equation. Like y equals mx plus b. But anyways, regardless, you can be able to, once you take the log, you can be able to magnify the differences. So you can be able to magnify the differences between and see what's really occurring. So you can look at the difference between 3 and 5 and understand that even when you're looking at the difference between 3 and 5 in the log scale, you're really looking at the difference between 100, like 10 to the 2x, right? So this is times 10x times 10, so this is a 100x difference, right? So you're looking at 100x difference in real numbers, but in the log system, you're simplifying it and just looking at the exponents, basically. And so again, log base, just simplifying magnitudes, normalizing it to a magnitude, and visualizing that number. That's why log base scales are useful. Not just originally, they were used to multiple addition, subtraction problems, but understanding really fundamentally what logs are and how they're the derivatives of exponents and how these graphs are working out as inverses of each other. This is a rapid increase, slow increase. This is a rapid increase in the beginning, slow increase later, and how they're really what log represent. And at the core of that, again, it's magnitude. Log is basically asking what magnitude of base, what power do you have to raise that base to be able to get this result x, what power do you have to raise this 10 to be able to get this result, what extent of base or magnitude of base is in this result. So all you need to know about logs is just know these 3 main aspects, know how logs can turn multiplication into addition, division into subtraction, know your log rules, understand the graphs, the exponential graph and the y equals log x graph, and be able to visualize how they look and how they're inverses of each other. And if you know these points, that can be helpful. And so the 3 things, again, know that they're multiplication into addition, division into subtraction, know the log rules, know the graphs, and then the 3rd thing is to know how their magnitudes, and that's this how their magnitudes, how many magnitudes of base fit in that number, what power do you have to raise this base to be able to get that result. At the core, that's really what logs are, just magnitudes, and normalizing to a magnitude, depending on what magnitude base scale you want, you can have different number scales and be able to understand different relationships. The log x relationship as the opposite and the inverse of the exponential relationship.
That was the all summary guide for logs, and thank you for watching.